Welcome to the comprehensive guide for Solidity interview questions focused on smart contract programming. Solidity is the primary programming language for developing smart contracts on blockchain platforms like Ethereum. In this series, we'll cover essential concepts including contract development, inheritance patterns, function modifiers, event handling, and advanced blockchain programming techniques. These topics are crucial for anyone preparing for blockchain developer interviews or seeking to strengthen their understanding of decentralized application development. Inheritance is a fundamental concept in Solidity that allows contracts to derive properties and functions from other contracts. There are four main types of inheritance in Solidity. Single inheritance involves one child contract inheriting from one parent contract. Multiple inheritance allows a contract to inherit from several parent contracts simultaneously. Multi-level inheritance creates a chain where contracts inherit from other contracts that also inherit from parent contracts. Hierarchical inheritance occurs when multiple child contracts inherit from a single parent contract. The syntax uses the is, keyword, and child contracts can access internal and public functions from parent contracts. Function modifiers are reusable code snippets that can modify the behavior of functions in Solidity. They serve four primary purposes. Access control modifiers restrict who can call specific functions, typically checking if the caller is an authorized user or owner. Input validation modifiers verify that function parameters meet certain criteria before execution. Reentrancy guards prevent malicious contracts from making recursive calls that could drain funds or manipulate state. State validation modifiers ensure the contract is in the correct state before allowing function execution. Modifiers use the underscore symbol to indicate where the original function code should execute. Events in Solidity provide a way to log information on the blockchain that external applications can access efficiently. Events have several key features. They store logs directly on the blockchain, making them permanent and immutable records. Front-end applications and external services can listen to these events to track contract interactions in real time. Up to 3 parameters can be marked as indexed, making them searchable and filterable. Events are significantly more gas efficient than storing data in contract storage variables. The emit keyword is used to trigger events, and they're commonly used for tracking transfers, state changes, and important contract operations. Gas optimization is crucial for creating cost-effective smart contracts. Several strategies can significantly reduce gas consumption. For storage optimization, prefer mappings over arrays when possible, as mappings have more predictable gas costs. Use uint256 instead of smaller integer types like uint8 or uint16, because the Ethereum virtual machine processes 32-byte words most efficiently. Declare variables as constant or immutable when their values don't change, as this stores them in the contract bytecode rather than storage. Choose external function visibility over public when functions are only called from outside the contract, as external functions are more gas efficient for parameter handling. Security is paramount in smart contract development due to the immutable nature of blockchain deployments. The checks effects interactions pattern is essential. Perform all checks first, update contract state second, and interact with external contracts last. Reentrancy guards prevent attackers from making recursive calls during function execution. For access control, always use MSG, sender instead of TX, origin as TX. Origin can be manipulated in certain attack scenarios. Input validation through require statements ensures that function parameters meet expected criteria before processing. These practices help prevent common vulnerabilities like reentrancy attacks, unauthorized access, and state manipulation. Comprehensive testing is essential for smart contract reliability and security. There are several testing strategies to employ. Unit tests focus on individual functions, verifying that each function behaves correctly in isolation. Integration tests examine how different contracts interact with each other, ensuring the entire system works as expected. Fuzzing involves testing contracts with random or unexpected inputs to discover edge cases and potential vulnerabilities. Code coverage should aim for at least 80% to ensure most code paths are tested. Popular testing frameworks include Foundry, which provides fast native Solidity testing capabilities with assertion functions and setup procedures. Proper deployment and monitoring practices ensure smart contracts operate reliably in production. The deployment process begins with thorough testing on testnets before mainnet deployment. Gas planning helps optimize deployment costs by analyzing contract size and initialization requirements. Source code verification on blockchain explorers like Etherscan provides transparency and builds user trust. Comprehensive documentation should accompany every deployment. Post-deployment monitoring involves tracking event logs to understand contract usage patterns, monitoring gas consumption to identify inefficiencies, watching for error patterns that might indicate issues, and planning for future upgrades or improvements to address evolving requirements. Security audits are professional reviews that identify vulnerabilities before smart contract deployment. The audit process follows several systematic steps. Documentation and code freeze establish the exact scope and prevent changes during review. Automated testing uses specialized tools to scan for common vulnerabilities and coding issues. Manual review involves line-by-line analysis by security experts who understand blockchain-specific attack vectors. The final report categorizes findings by severity levels. Critical vulnerabilities threaten protocol safety and user funds. Major issues involve centralization risks or logical errors leading to fund loss. Medium severity problems affect performance or reliability. Minor issues involve inefficient code patterns that don't compromise security. Success in Solidity interviews requires mastering core concepts and demonstrating practical experience. Focus on fundamental topics including inheritance mechanisms, function modifiers, event handling, and security patterns. Be prepared to write and explain code snippets during technical discussions, as interviewers often test hands-on coding abilities. Develop strong security awareness by understanding common vulnerabilities like reentrancy attacks, integer overflow, and access control issues, along with their mitigation strategies. Master gas optimization techniques to show you can write efficient, cost-effective contracts. Practice explaining complex concepts clearly, as communication skills are valued alongside technical expertise in blockchain development roles.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.